Welcome to Excel 2010 Statistics video number 30. Hey, if you want to download this workbook, Excel 2010 Statistics Chapter 3, click on the link below the video. Hey, in this video, the title of this video is Standard Deviation. How fairly does the mean represent its data points? So we've been talking about mean a lot. But if you have a number of means and you're comparing them, we can't really do it without talking about the concept of variability. Now, there's a couple measures that we'll use for calculating variability, but the one most common use and the one we'll use throughout this class the most is standard deviation. Now, variability is the main point of this video. Let's look at an example of a mean calculation that'll help us jump in and really understand what variability means, because it's hard to understand what variability and standard deviation means without talking about what the mean means. Let's go ahead and calculate a mean. We have stock A and stock B. So I'm going to calculate equals average. Highlight that range there. Those are relative cell references. So I can Control-Enter and copy it over. Right, so that we got our two. What? They're both on average from our past data, returning an average of 4.1% return per year. So which do you prefer, stock A or stock B? To answer that question, we have to actually look at the individual data points and determine what the variability or the dispersion is. Now, you can see here, I don't see any negatives at least. Right here I see some negatives. Here, these all seem to be clustered pretty close to the average. Wow, these ones seem to be pretty spread out. Lots of variability. But we can't just eye it. We're ultimately going to do a numerical calculation to calculate variability and dispersion. But let's go look at a picture. Sometimes a picture tells 1,000 words. I'm going to click on V2. And here's our two stocks, all the data points, A, B. 4.1, 4.1. And now let's look at this picture. Stock A. Here's plotted the individual return. So here you can see we have like a minus 23%. Up here it's like a positive 20. And right here is the mean. Stock A mean is right there. So that's 4.1. Right? So these data points are pretty spread out. Here's stock B and all of its data points. Stock B mean, oh, it's exactly the same, about 4.1. And here's all the data points. They're not as spread out. So variation or dispersion or spread in the data can be seen visually. Now, variability, also you'll hear the word dispersion. It's really just what is the spread in the data? How spread out is the data? An important question that variability answers is, are the data points clustered around the mean? Well, here's my 4.1, right? So any given year, I'm not going to have any big losses or big gains, but they're all going to be right around 4.1. Here, on any given year, wow, I might have a huge loss or a huge gain. Now, a measure of variability like this for stocks measures risk, right? For this stock getting 4.1, I run the risk of getting something way out here or way up here. Right? So how are the data points clustered around the mean? They are for this one, so right, and not for this one. Even more importantly, our measures or our visual portrayal of variability answers the question, does the mean fairly represent the data points? Well, notice this is 4.1, and all of the data points here are pretty close, right? They're all about 4.1. But now let's ask the same question here. Does this mean fairly represent its data points? Well, it's 4.1, but what about this one? Does 4.1 return fairly represent a minus 22%? No way. The actual distance between these two is called a deviation. So remember, what's the point of a mean? We have one number that stands in and represents all the numbers. We then use that number in discussions or calculations, right? 4.1. Well, if you're going to use 4.1 to represent this one data point here, it's not fair at all. So dispersion is incredibly important when you're using means, right? How do we compare these two? Well, we ask the question, what's the dispersion? Now, this is a visual chart, and we'll see how to create this at the end of this video. I want to go look at 3 measures to measure our variation or dispersion. Always remember that ultimately we're deciding, are the data points clustered around the mean? Yes. No. Does the mean fairly represent the data points? Here it does. Here it doesn't so much. All right, I'm going to go over to the sheet. We're actually going to come back to V3 at the end of the video and create that chart. I want to go over to V4. Again, we're going to answer the same questions. We're going to look at our first 2 measures of dispersion. The first one is range, right? Max minus min. It's simple to calculate, right? Then we see the numbers between the max and the min called the range. It's very sensitive to the smallest and largest data points, extreme values. And it only uses 2 points. No problem. It still is useful. I'm going to calculate the max for stock A. Control Enter. And I'm going to drag this over. Notice that that blue box, they're all relative cell references. So when I copy this over, it moves over there. All right. Oh, OK, so the max is 19. Well, that's great. I'd love to earn 19%. Oh, the max here is only 5.5. I don't know. Well, let's do the min. I'm going to do stock A first. Control Enter. And then copy it up. Oh, minus 20. I wouldn't want to have a minus 22% return for a year. Oh, and the min here is only 2, so we really never get into negative territory. Now the range equals, well, it's always going to be the max minus the min. And then I'm going to copy this over. Those are relative cell references. All right, so the range here is gigantic. The range here, much, much smaller. So which one has more dispersion based on the range measurement? Obviously, stock A. All right, well, the limitation of this is it's only using the biggest and smallest. For example, what if there was only one really small one, but all the other ones were clustered? So this is useful. We can see the range, but it's only using 2 values, and that has its drawbacks. Now, let's talk about interquartile range. This deals interquartile range. We already saw it with our box plot. Quartile 3 minus quartile 1. What it will tell us is the range for the middle 50% of the data. It overcomes the sensitivity to extreme values. So let's calculate quartile 1. I'm going to use quartile.inc. I'm going to get all of my cells right there. And I'm actually going to copy this down because I want to calculate quartile 1 and quartile 3 for stock A. So I'm going to hit my F4 key and lock it. And now I'm going to comma. And I put my 1 and 3 here, so I'm going to click on the relative cell reference. So I'm going to copy down. All right, so for stock A, we have quartile 1 is still a little bit minus. Quartile 3 is 0.11. Now let's do the same thing here. This is for B. I'm going to hit F4, comma. Now notice the formula is hanging over here, and I want to get that 1. There's a couple ways we could do it. One way is to use your right arrow key. Now you can see the right arrow key got H21. Sometimes your right arrow key doesn't work because you're messing around with the formula. And in that case, you can click right there and then down arrow. All right, Control Enter. Now interquartile range is just the range for the middle 50%. So I'm going to say equals the bigger one, quartile 3, minus the smaller one, quartile 1. So with this measure, we're eliminating some of the bigger values. We get 0.115 and 0.01, so about 11.5% if we were to format that, or about 1.5 0.1% if we were to format that. So here we can, in both of these measures, see that the variation or dispersion or spread in the data is much greater for stock A than stock B. All right. Now we want to talk about a numerical measure to calculate variability or dispersion that uses not just a few of the values, but all of the values. Let's go back to the sheet V2. Now, let's think about this. Here's the mean, and here's the individual data points. We're trying to come up with a measure to calculate variation. Well, think about mean. What did we do with mean? We actually used all the numbers. We added them all up and divided by the count. That gave us the average return, right? Well, what if we could do the same thing with dispersion or variability here? Let's think about this. Here's the average or the mean. Then there's this point. We could compare this to this. And what do we get? Well, it looks like this one's a little below. So that particular value is a little bit below that one. So if we calculate the difference, that'd be a negative. What about this one? This one's way below. If we calculated the difference, what's called deviation would be a big negative number. What about up here? Well, this value is way above the mean, so the deviation is positive. What if we could actually calculate all the deviations and then average them? That's what we're going to do. Now, you could just imagine, right? We do have to deal with the fact that there's a bunch of negatives here, but we'll do that by squaring the deviation. But imagine if we could take the distance here, and 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 average them. Well, I bet you anything that the average for these distances would be much smaller than the average for these distances. Again, mean, individual particular values. If we calculate the deviations for all these, add them up, divide by the count, this is going to be very small. This one's going to be very big. And that's the essence of calculating standard deviation. So let's go over and see how to do this. I'm going to click on the sheet V5. Now, what I've done is I've set this up. We have stock return for A and B. And we're going to calculate the deviation. Remember, what is the deviation? It's just, hey, the actual particular value minus the average. So that means before we can calculate the deviations, we have to calculate our average. Now, this is from sample data, so we're going to call it the mean is x bar. We're going to calculate all of our deviations, and then we're going to have to do a couple calculations with those. But the essence is we're going to be calculating a type of average of all the deviations. And this type of average for deviations is called standard deviation. Now I'm going to use SD, sample standard deviation. Oh, deviations, standard, it's kind of like taking an average of the deviations. Now the symbol we'll use for sample is S. We'll actually use sigma squared. And over on V6, there's our formulas for variance and standard deviation that we'll be using. But here's our standard deviation. This is the main measure that we'll use for variation or dispersion. We're going to take, let's look inside here. Sigma, there's x sub I. That means your particular x minus x bar. Oh, that's a deviation. So a deviation is going to be the actual particular value minus the average. Actual particular value minus the average. Actual particular value minus the average. Remember, visually, it's the distance between each particular value and the mean. Right? So up here, that's what that is, deviations. And you have to calculate all of them. Now, because there's going to be some negative ones and some positive ones, or said a different way, if we go to our visualization here, there's going to be some below and some above the mean. We're going to run into trouble with averaging it, and I'll show you the exact trouble we'll run into. But that means we're going to have to square it. Now, no problem. We're going to square it, and at the end, we'll take the square root, which actually undoes it. So the top of this formula, just think of it as, hey, those are all the deviations. And in the denominator, we're going to divide by the count. Now, why do we have to minus 1? Sample data divided by just the count tends to underestimate. And so to compensate for that, we do n minus 1 for a sample. Now, what does minus 1 do? If you think about this, what's 10 divided by 5? It's 2. Now, what if we subtracted 1 from that 5? It would be 10, 5 minus 1. 10 divided by 4, it's 2.5. Oh, so what does that minus 1 do? It actually pushes up the result just a little bit. So if sample data divided by the count tends to underestimate, then the minus 1 is an adjustment that brings up the number just enough to make it more accurate. All right, so that's our formula. That's a pretty fancy formula. Let's see how to do this. Now, for each stock A and B, we're going to have to make our calculations. Now, we're going to have to count. So we're going to use the count function. Enter. Equals that minus 1. That's going to be our denominator. And then our average. Right? And in your homework, you'll have lots of data sets just like this, and you'll have to make these exact calculations. Now, let's calculate the deviations. Now, in the old days, before we did in Excel, this was the brutal part of standard deviation. You'd have to take out your handheld calculator, type in all these numbers, and subtract this mean all those times here. But in Excel, what do? Equals one cell to my left, relative cell reference, minus the mean, and I'm going to lock it, F4. That F4 locks it. So when I copy it down, Control-Enter to enter it in. And then I'm going to point to my fill handle when I see my little angry rabbit. I'm going to drag it down. Those are all the deviations. Now, normally what we do is we'd simply add them up. Because we have a bunch of numbers and we want the average, right? Add them up and divide by the count. Let's see what happens when we add these up. I'm going to click in the cell below. Alt equals is the keyboard shortcut for AutoSum. Enter. 0. 0. What is that going to do? That will happen every single time. The sum of the deviations will always equal 0. You have some below the mean and some above the mean. Here's above, 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 below, 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 above. So there's some above, some below. So when you add them up, you always get 0. And we'll prove that over here also when we calculate them for values that are more clustered together. Because some of these will be above and some of them will be below the mean. Right? The only time that that wouldn't be true is when they're all exactly the same. Right? Well, that'd still add up to 0. All right. So that's the reason that we have to do something. Now, there are other calculations. For example, you could take the absolute value and then average these. But standard deviation is the most common measure used. So that's what we're going to do. We're going to take each deviation and Shift 6 to get the caret, which is exponent 2. And then I copy it down. Check the last one, and there it is. Now, the total of all these deviations squared, that's this part right here, the top part of this division, the numerator. So I'm going to add all these up. Alt equals. All right. And now we're going to calculate something called variance. This is sample variance. So it's all variance means is it's before we take the square root. So here we go. Equals the total of all the deviations squared divided by our n minus 1. That measure is called variance. And it can be used to compare to our other data set, and we come to the same exact conclusion. The only problem is the units are squared because we squared it up here. So we have squared units, which doesn't really make much sense. So what we do is we take the square root. And really what that does is it undoes this and gets it back to just a single unit. So I'm going to take the square root. So you could use the square root function. and then Control Enter. There's our measure. Sample standard deviation. We'll be using this measure all the way to the, in every single chapter moving forward. We'll be using mean and standard deviation. The standard deviation tells us how much spread in the data. Are the data points clustered around around the mean or not? Now let's go ahead and do this calculation for stock B equals count equals count minus 1 equals the mean deviation. All right, and I have to lock that one with my F4 key. Add them all up. Alt equals, and there it is, 0. That's why we have to do something to these, because we can't add up all the deviations. So we're going to square them. All right, so there we have our square deviation. The fact that we squared it means at the end we're going to have to take the square root. All right, so ready? We're going to add these up. Now let's calculate variance, sample variance. I'm going to take the sum, and that's the sum of all of these square deviation. That's this part, divided by n minus 1. That's this. And now we need to take the square root. But we can see very clearly the variance. We can compare these two here. Now this is in scientific notation here. We can Control 1 to format the cells, or go up. Actually, we could go up here to number. But that's not going to do me much good. So I'm going to use the either this dialog launcher or Control 1. And I'm going to do something, and I'm going to watch the sample here. All right, so which one is bigger? This one's much bigger. And we can clearly see from variance that stock A has much more dispersion in the data. Let's go ahead and calculate our square root. Actually, I'll show you a different way. You can say this and caret 1 divided by 2, right? A fraction in the exponent means takes the root, the second root. You could use the square root function too, just. And there is standard deviation 0.00945, and this one is 0.11. So this just has a lot more spread in the data for stock A than for stock B. It means there's more spread here, less spread here. This is bigger, so the values are spread out. This one is smaller, so it means all the data points are clustered around the mean. And if the data points are clustered around the mean, it means the mean more fairly represents its points. Let's go back over to V3A or V2, whichever one. The same chart is there. And there it is. So now we have a numerical measure. Our numerical measure for this stock B showed us that there is much, much less variation in the data points here than there is for stock A. All right, so standard deviation. Just a great calculation. Now, of course, we're not going to, in this class, I want you to do it a couple times to prove to yourself, because the math of it really helps reveal the meaning of it. We really are taking a type. We're figuring out what all the deviations are, and then taking a type of average called standard deviation, right? OK, so but once you do it a few times, and by the way, on the test, I will have you do it longhand once, and then I'll have you do it a bunch of times with the formula. The formula we're going to use is ST for standard, DE, and there's a standard deviation dot P and a standard deviation dot S. So which one's for the population? Which one's for the sample? This one's for the sample. And all you have to do is highlight the actual values. stdev.s does all of that work instantly. Now I'm going to do the same thing over here, stdev.s. Pretty awesome. Now we definitely want to do all the math because it helps reveal the meaning and how it works. But once you get the hang of it, it's a lot easier to use stdev.s. Now the sample standard deviation, these two, is a point estimator for the population SD. And we'll do more with that later. Here we're comparing these two, and we can clearly see that as a measure of variation, this stock has a lot. This is a sample, so we don't know the exact population parameter. This is a sample statistic, but it is our best estimate of what the population parameter can be. Now, in this particular example, stock returns. As you can imagine, the standard deviation is a measure of risk in a stock, the volatility. Now, in this example here, if we go back to V2, right, you can just imagine on any particular, if you invest in this stock, right, you're expecting 4.1. But on any particular year, the risk is gigantic that you might have, a huge loss or a huge gain. Here, not much risk, right, at least based on our past data. All right. And finally, the very important point here is which mean more fairly represents its data points. Well, clearly this one here, because the standard deviation is much less. Now I want to go to this sheet V6. And on V6, I just want to compare the calculation for population standard deviation and sample. Here are our formulas. And I'm going to zoom in on this over here. And I'm actually going to do something really terrible here. I'm going to calculate our sample variance and sample standard deviation, and then calculate the variation for population and standard deviation from sample data. But all I want to show you is the difference in that n minus 1. Now, sample variance is s squared. It's just the step right before you take the square root and calculate your s. But we're going to use the VAR. And just like for standard deviation, there's a VAR for the variation for population and sample. So I'm going to do sample. And these are relative cell references. So I'm going to Control-Enter and copy it over. All right, so we can clearly see from our sample data here, and this is sample data, sample 2 has much more variation. All right, let's go ahead and calculate our standard deviation. Now, if you had this calculation, you could just take the square root of that. But stdev, and there is a p and an s. So when we calculate our standard deviation, we're always going to come to the same conclusion. But standard deviation is much nicer because now we don't have those squared units. Now, we wouldn't use var.p and standard deviation.p on sample data like this, only on population data. But I do want to show you that the calculation, the only difference is that for sample data, we do n minus 1. And for population, we just do n, no minus 1. So there is a difference here. This is with the population calculation. Only difference is we didn't subtract 1 in the denominator. Here we did. So you can see the point of this is you can see that it bumps it up a little bit. And for sample data, that is important. Equals, and then this one right here, that blue box will move if we copy it over. So you can see clearly from 33 up to 41, and then the standard deviation also. I don't even think there aren't very many homework problems for population data, even in the textbook. And I don't think I assigned any. So again, here it is. By doing the n minus 1 up here, it bumps it up a little bit to make up for the tendency of sample data to underestimate the population parameter. Now, one last tab. We want to go to CV for coefficient of variance. And we want to talk about our last measure of variation or dispersion. Let's look at a situation here. We have stock return on 1, 13%, and the standard deviation is 20. Stock return 2, 17. Wow, that looks much better. I'd rather have 17% return over 13. Oh, and then standard deviation. Ooh, already. You can see, yeah, the stock return is higher on average, right? But the standard deviation is a lot higher. That means the dispersion, the spread in the data is going to be a lot bigger. And then here's stock 3. We have a 6% mean return, and then here we have standard deviation of 8%. So how do you decide between these? Well, we can calculate coefficient of variation. Coefficient of variation converts the standard deviation to standard deviations per unit of mean. Now, we can use coefficient of variation to compare data in different units, which we'll do in just a moment, or data in same units, but means are far apart. So our means are far apart. And we want to know which one relative to each other has the most or least variation. So what we do is we divide. We're going to take sample standard deviation divided by x bar. Now, anytime you do division like this, standard deviation of the sample divided by x bar, when you get the answer, there's always a 1 in the denominator. So it'll really tell us for every 1 unit of x bar, which is our return, for every 1 unit of return, what's the variation or sample standard deviation. So I'm going to say equals, and it's sample standard deviation divided by this. Now we're doing division, so the result is 1.58. 1.58 for every 1 unit of estimated x bar return. So I'm going to copy this formula down. Right? And so it is a way to compare when we have different means, compare our variation. Here, 1.5, 1.9, 1.3. So clearly, the coefficient of variation, which tells us the relative variation or standard deviation, is highest for stock number 2. Now, the way I like to think of it is for every 1% of return, because remember when you do division, there's a 1 in the denominator. For every 1% of return, we have 1.94 standard deviation. That means that one has the most risk when you're talking about stocks. All right, so that's one example of coefficient of variation. Now I'm going to scroll over here. Another use for this is when, let me make it a, whoops. We can compare relative variability in 2 distributions. Well, here we have mean bonus paid per employee, and then the standard deviation. Here we have mean years worked and standard deviation. These are completely different units, right? And so how do we compare them? Which set of data has the most variability or dispersion? Well, let's do our coefficient of variance. Coefficient of variance. We're going to take standard deviation divided by our mean, 38%. And here it would be standard deviation divided by our mean. So which of these 2 data sets has more coefficient of variance, which is really our measure of variation? Clearly, this one. There's more variability relative to the mean in the distribution of bonus paid compared to the distribution of years worked. So that's a way of comparing variability when either the data are in different units, like here we had dollars and years, or data in the same units, but means are far apart. All right, that was a lot. Oh, actually, we have one more topic. I want to show you how to make that variability chart. I'm going to go over to the sheet, actually V2, and look at this chart. Now, we're going to create the chart on V3, but let's think about how in the world we do this. Now, here's all of the data points for stock A, and here's the mean. These data points are really only plotted on one axis, right? This means we had 22, minus 22%, minus 15%, 1% return, 19% return, right? This is the average plotted right here. So it's about 4.1, and that's 4.1, and all those ones are right in this range here. So how in the world would we do that? Well, we're actually going to have to do what we usually do with Excel charts and trick the chart wizard. We're actually going to plot this on an XY, even though there's really not two variables. I'm just going to plot. Well, let's think about when you do XY plots. How in the world could you get all of the X values on the same line? Well, that just means that Y would have to be the same for all of the points. Because remember, what is an XY scatter? It's out a certain amount and up. So every single one of these is out, and the same number for the Y every single time. So we could do 1, 2, 3, 4, or 0.5, 1, 1.5, 2, whatever we want. So let's go over to this sheet V3, and I have our returns for A. And what we want to do is we want to put a number here. Now, let's look at this. I actually want to reverse this. I want to put A on the top and then the mean right below it. So really, that would have to be 4, 3, 2, 1. So I'm going to put a 4 with all of these. Remember, for an XY scatter, you have an X and a Y. We just want all the Y's to be the same. Now, I'm going to do a little trick here. I'm going to highlight all the whole range. And in the active cell, I'm going to type the number 4. And to populate, to put that thing into all the cells, hold Control and tap Enter. All right, so that's 4. This is 3. This will be 2. So 2, Control Enter. And then this will be 1. All right, now let's go ahead and try and plot this. I'm just going to go like this. This first X and Y, go up to Insert, Scatter, and Scatter. That's our starting point. We'll have to clean this up a bit. I'm going to delete these lines. I'm actually going to delete that axis because we don't need that. Now I'm going to click and drag on this edge to drag it down over here because we need to add data and I need to access all of these. I'm now going to go up to Chart Tools, Design, Select Data. This is the real power of charting. Now I can add. I'm going to click Add, the series name. I'm going to add this mean there. The X value will be this. And the Y value, you've got to highlight that and delete it, and then click there. Click OK. You can sort of already see those two right there. Beautiful. Add. Series name, I'm actually going to click right there. X values there. Y values, I'm going to highlight that and delete. Now, I can't quite get to it the way I could there, so I'm going to click there, and I'm going to use my keyboard shortcut, Control-Shift-Down arrow. That's a great trick to highlight data behind a chart. Click OK. And then finally, Add, Series Name, X value, and Y value. Delete, and then click right there. Now, this is click OK, click OK. This is totally messed up, but we'll fix that in just a moment. There it is. Now, if you don't like that, you can click on it and then right-click Format Data Series or Control-1. Marker Options. Say that, built-in or whichever one you like. Now, this is all, these are links. So now I'm going to come up here, and I'm going to call this the XY scatter always takes the label from the Y. I'm going to call this stock values for A. Ah, that's looking good there. Mean stock A. Mean stock B. And then stock. I'm going to put returns for B and change this over here. Now I'm going to click here and Control-1, show at top. And there we have a visual portrayal of our stock A. There's all the data points and the mean for stock A, all the data points for stock B, and the mean for stock B. Now, the whole point of this video is variability and standard deviation. So variability, you want to think of it visually. If you're having a hard time grasping, here's the mean, here's all the data points. So variability, usually measured in standard deviation, asks the question, how fairly does the mean represent its data points? In this case, this one clearly more fairly represents its data points because all these data points are much more similar to this one. Here they're all spread out. The other way to think of it is how much spread is in the data. Much more here, much less here. How clustered are these data points around the mean? Much more clustered here, much less clustered here. So there's our chart, our visualization of variability. And if we go back to our V5, the standard deviation, that is the calculation. And you want to think of it as just, hey, take all the deviations and do some sort of averaging. Technically, we're going to do it mostly for the sample, so we'll use the little s, sample standard deviation. Square all the deviations, add them up, divide by n minus 1, take the square root. Or we just, after you get the hang of it and you know that it's just some sort of way of getting a typical type of deviation called standard deviation, then you use stdv.s. All right, I'll see you next video.